out here. Boom, boom. And we are live recording. Yes, so welcome to our Columbia Basin Geologic Society and then the Department of Geosciences at Eastern Washington University. A lot of people know Scott for his wonderful publications with a whole group of wonderful people from the Yakima Fold and Thrust Belt. But then I know at Geological Society of America meeting a couple of years ago, I saw a great presentation on the Mount Hood Fault Zone. So I'm really excited to have Scott here. Did his BS at Northridge, a master's in North Carolina. So he's got both coasts down. That's why we have such a diverse audience here today. And then of course a PhD in Davis, and it has been done some consulting, but most have been with the USGS, and has really built a wonderful respect from people due to his field work ability and trench work, and great publications. So I'm super excited to have Scott Bennett here. So without further ado, thank you.
Thanks, Chad. Well, yeah, I appreciate the introduction and the invitation to share with you some research in what I've been working on recently in North Central Oregon. For those of you who don't know me, well, like Chad said, my name is Scott Bennett. I'm a research geologist with the USGS in Portland, Oregon. And today I'm going to summarize some recent geologic mapping and paleoseismic trench research that constrains the timing of the most recent large earthquake on the Mount Hood Fault Zone in North Central Oregon. I will share some findings that will begin to answer some questions about, what's the fault slip history? What is the recent earthquake activity? And what string of cascading hazardous events might have occurred only a few centuries ago as a result of strong shaking from a really recent earthquake? Some of what I will share today during this talk can be found in a GSA field trip guidebook that we just published about a month ago related to the GSA meeting that was held in Portland in October. I'd be also remiss to not acknowledge the long list of collaborators from the USGS, Portland State University, the Oregon Department of Geology, DOGAMI, and various other collaborators that have been involved in parts of this research I'll be sharing with you today. So just to kind of dive into kind of a regional tectonic setting, a lot of you are probably familiar with this, but I'll go over some of the basics. The Pacific Northwest region of the United States is dominated by the Cascadia subduction zone, a plate boundary where a Juan de Fuca plate is subducting beneath the North American plate obliquely at about 30 to 40 millimeters per year. This oblique subduction, as well as motion related to the Pacific North America plate to the south, is driving a series of clockwise vertical axis rotation in this upper plate of North America, rotating around some sort of pole, if you're familiar with Euler poles, in the back arc of the Cascade arc. So specifically, the part of the Pacific North America plate boundary that's driving this is the Walker Lane, the belt of transtension on the east side of the Sierra Nevada mountains. That's driving the Sierra Nevada Central Valley block into the Oregon Coast Range from the south and driving this block around the corner and rotating around this pole. So a lot of deformation happens as a result of all this complicated plate tectonics, which includes the northwest translation of the Sierra block that I mentioned, this northwest translation and rotation of other crustal blocks like the Oregon Coast Range here, this pink one, intra-arc extension within the actual volcanic arc, which will be the main focus of the talk today. And behind that, and the kind of the trailing edge behind that, is a lot of basin and range extension. And of course, the northern part of the arc is kind of a compressional arc as things kind of slam into the Canadian coast mountains here. Faults like the Doty Fault and the Seattle Fault and the Leech River Fault and other active faults on Vancouver Island all accommodate a bunch of north-south shortening, sometimes oblique shortening, and transpression across this zone here. And of course, where a lot of you folks are residing, you're also familiar with the shortening related to this kind of regional tectonic setting in the Yakima Fold and Thrust Belt on the east side of the Cascade Range. So another perspective that I like is this recent paper by Tom Broker, who published this in 2017 in Tectonics, which has a slightly different location for a rotation pole. But Tom and his co-authors tried to summarize a lot of kind of geologic and tectonic features like fault zones, strike slip faults, and normal faults and thrust faults, and combine that with analysis of the focal mechanisms of earthquakes around this large part of the continent, and try to come up with a single kind of theory, single model that kind of helps to explain a lot of the observations. So not just the shortening we're seeing in the Puget Sound area and the Yakima Fold area and the strike slip faults, these arcuate strike slip faults, but also a lot of the extensional faults that go all the way back into Montana, Idaho, and Utah as in one kind of unified model for the tectonic makeup of this region. So the way to look at this model is, imagine that there are things rotating around a pole up here. Any faults that are parallel to these small circles, these dashed blue lines, you predict them to be strike slip faults. Any of the faults that are, perpendicular to that, so for example, one of these Yakima fold and thrust structures, those would be kind of a dip slip fault, either compressional or extensional. So that's kind of how to think about this kind of regional model for the Pacific Northwest. And, we have three major types of earthquakes here in Cascadia. One's on the subduction zone interface, magnitude 8 and 9 down here. Large earthquakes like Nisqually in 2001 that are accommodating strain within the downgoing slab, and these crustal earthquakes that occur on these faults in the upper part of the North America plate. And this is kind of the focus of a lot of my research, is understanding how these faults accommodate deformation on the plate boundary and what's the hazard related to these earthquakes. So let's zoom into kind of the Oregon component of the plate boundary. And here we'll zoom into kind of the Hood River Valley here, just south of the Columbia River, which is located along the axis of the Cascade Range. The Cascade Range, of course, is a chain of Quaternary and Pliocene volcanoes that stretch from Northern California, Lassen and Shasta, all the way up through Washington to southern British Columbia. This graben is a kind of 20 to 30 kilometer wide, kind of discontinuous and structurally segmented graben that has formed as a result of kind of the northward propagation of rifting, where volcanoes and faults started maybe around 7 or 5 million years near the latitude of Bend, and are getting progressively younger and younger as you go towards the north. And that's been interpreted by folks like Rick Conry as a northward propagating rift. And so let's zoom into the area of like north central Oregon here, where we can kind of see that. Let's look at the topography here. You can kind of start to see the topographic expression of this north-south oriented rift with these large kind of fault-bounded valleys here, and near Mount Hood, right here, you kind of see like the topographic expression of this north-south oriented graben. And zooming in even farther to the Columbia River Gorge area, you can kind of see that, again, the topographic expression of this north-south oriented graben here, especially on the east side here. And so the Columbia River Gorge is probably most of you have driven through or visited many times, is this very dramatic and scenic topographic and geologic phenomena where the Columbia River has carved its way through the Cascade Range on its way through Portland and out to the Pacific Ocean. This is kind of a classic view from the Columbia River Gorge, where you have steep vertical cliffs with tons of waterfalls cascading over them on the Oregon side. So this is looking west down the Columbia River. And on the Washington side, you have kind of more gentle slopes that are dominated by a lot of landslides due to the gently south dipping dip slopes on the Washington side of the gorge. And so a lot of this work is currently being mapped by myself and several of my colleagues at the USGS and state agencies like Dogami under a program called the USGS National Cooperative Geologic Mapping Program. And the components that fund the USGS is called FedMap. And the program that funds state geologic surveys like Dogami or Washington DNR is called StateMap. And of course, there's funding for students to do geologic mapping research called EdMap. And a quick side note, I'll just say that people who pursue StateMap and EdMap funding, be aware that there's going to be a big bump in both of those programs in the very near future, thanks to new congressional funding to the National Cooperative Geologic Mapping Program. Okay, so here's kind of what we've been mapping. The red polygon in the background here is the Columbia River Gorge National Scenic Area that kind of straddles the Columbia River. And so our goal is to map the 7.5-minute quadrangles that kind of straddle and encompass this National Park Service entity. And so this is kind of a status map showing the maps that have been published and who's mapping them, USGS and state and Dogami. So let's zoom into the Mount Hood Fault Zone. And this map I'll come back to many times during my talks. Let's get a little familiar with this map. It's just a hill shade of the topography showing some of the structures. And some of the important structures here is the Mount Hood Fault Zone, the Hood River Fault Zone on the east side of the Graben, which is kind of a west side down fault system. And on the west side of the Graben is the Mount Hood Fault Zone. It consists of at least 3 fault segments that were first discovered in LiDAR topography about a decade ago. Each one of these colors shows these fault segments, and these are basically LiDAR mapped, very youthful scarps that we can see in LiDAR and also confirmed in the field. So what is a segmented fault? Well, fault systems commonly consist of several shorter fault segments. In this kind of schematic diagram here, this fault composes of this kind of imaginary fault system consists of 4 strands, and they're separated by either fault stepovers or a place where the fault takes a major bend, or maybe a cross fault comes in and intersects this fault system. And it's thought that the rupture length of any single earthquake can be limited in most cases to maybe one or a couple segments of a larger fault system, and not the total length of the entire segmented fault. So what does this mean? That means that if you look at a plot of kind of magnitude versus the length of any single earthquake rupture, there's been demonstrated very well for several decades a strong relationship that the longer a surface rupture is, the larger the earthquake that you will experience. Earthquake magnitude, of course, is a hot topic for a lot of people, including folks in Hollywood. One of my favorite movies to complain about is San Andreas, a recent Hollywood mega hit starring The Rock, which had, I think, a couple 9.1 earthquakes in the same week or something like that. Here's a docu-series that was a kind of a B movie called 10.0. And there's even things on, TV dramas like this one on NBC, 10.5 magnitude. Can you imagine that? Look at this one. It looks like it involves the Space Needle, the Golden Gate Bridge, and Southern California. So that sounds like a pretty big earthquake, right? Oh yeah, I even recently found this great one, an 8.5 earthquake on the cover of a 1970s power rock pop album in a thrift store recently here in Portland. And yes, I did buy that. I did go home with that album. It's not that good. But let's actually think about what that means, like a magnitude 10 or 10.5 earthquake. If you extrapolate this empirical relationship diagram, if you were to ask yourself, how long would an earthquake rupture need to be for a magnitude 10 earthquake? Because this is a logarithmic scale on the surface rupture part of the diagram, you would need a fault and rupture that's 20,000 kilometers long. What does that mean? That requires a fault that goes from the North Pole all the way around to the South Pole. So next time you're hanging out with your family and you talk about you're a geologist and you're talking about earthquakes and earthquake magnitude, a fun fact to share with people is that there's no such thing as a magnitude 10 earthquake thanks to this logarithmic scale. It would require a fault that wraps halfway around the Earth, and no fault exists on this planet. So segmented faults happen in all types of tectonic settings, from compressional settings like subduction zones, where these red circles here show the kind of patchiness of the part of the subduction zone that ruptures in South America. The San Andreas fault is thought to be segmented and ruptured independently, segments and rupture independently of each other. And faults in extensional systems like these in normal faults in Hawaii are segmented in this nice oblique view as well. So let's turn back to the Mount Hood Fault Zone here in North Central Oregon and talk about some of the scientific questions that I'll address today in my talk. Some of them, so I want to kind of inquire about when the Mount Hood Fault Zone initiated, when was the most recent earthquake, and what was its magnitude? And are surface rupture earthquakes restricted to one of these fault segments here? Do the earthquake ruptures, are they limited to, say, this northernmost segment where they stop at the north and south ends of it? Or does it go through this what we think is a segment boundary and involve more than one segment? Or can it go through all of these segment boundaries and go from all the way from the southern to the northern tip of this 55, 60 kilometer long fault zone? And other scientific questions, can earthquakes in the Mount Hood Fault Zone cause landslides? We've seen tons of landslides in the Columbia River Gorge here. And finally, kind of put this fault zone in the kind of the regional context for the understanding of its role in the tectonic framework of the Pacific Northwest. So let's dive into when did this fault zone initiate and how much offsets happened on it. So in the Columbia River Gorge, we have small exposures, but mostly unexposed Oligocene Eagle Creek Formation related to the early parts of the Cascade Arc. But basically above river level, we start off with Columbia River flood basalt group deposits, Grand Ronde and Wanapum basalts primarily. And folks in the eastern part of Washington are probably very familiar with these units. I'm not going to go into them in too much detail. But overlying those is a sequence of Pliocene lavas called the Late High Cascades lavas. And these are dominantly consist of these low potassium tholeiitic basalts. And I'll colloquially refer to these as kind of LKT lavas that are Pliocene in age. And on top of that, we have a smattering of quaternary stuff like glacial deposits, smaller volcanic eruptions, and other superficial deposits like colluvium. So let's zoom into the Columbia River Gorge here and show some of those structures here. Here's the Mount Hood Fault Zone coming along the west side of the Graben. So here's the Hood River Fault Zone on the east side of the Graben. Here's the Columbia River. And the next slide I'm going to show you is a perspective looking from Washington, looking south at the same topographic data. And you can kind of see how the Columbia River has carved through this and formed this dramatic landscape to Columbia River Gorge, where the cliffs of the gorge go from basically nothing near Troutdale, Oregon, and climb gradually to their highest elevations, highest relief near Cascade Locks, and then drop back down to basically no cliffs again near the Hood River Valley. You can kind of see this kind of arched anticline nature of the Columbia River Gorge here. And here's that slide I showed on my title slide, kind of looking at an oblique perspective of that same topography. And we'll come back to this a little bit later. So let's zoom in once more and let's switch into some more detailed topographic data. Now I've switched to start showing you LiDAR data. And the northern end of the Gate Creek Fault segment, which is the northernmost segment of the Mount Hood Fault Zone, intersects the steep Oregon cliffs of the river of the Columbia River, where its surface trace is easily apparent in this hillshade of 1 meter LiDAR topography. Here, the Gate Creek segment is a north-northwest trending subvertical fault with east side down offsets visible in all Miocene and Quaternary units. A common approach to look at active faults is to look at a hillshade, but another common approach, so this hillshade shows kind of a lighting direction from one direction. But another common approach, sometimes more powerful, is a slope shade map. This is the slope shade of the same area. It's a little challenging to kind of comprehend if you're not used to them compared to a hillshade. But here, the slope shade shows the differences between steep areas like the cliffs in dark and less steep areas like this top of this plateau in brighter shades. And so the scarp and the resistant geologic units stands out really well in a topographic slope shade. Okay, zooming in further, here's again the Gate Creek Fault. Sorry, I got a little bit of a lag here in my pointer. Again, you can see kind of the topographic scar across the landscape here, this north-northwest trending scar. And so when did this fault initiate? So we can kind of think about this, test this through geologic mapping. To determine the timing of earliest faulting, we compare the magnitude of offset in the 16-million-year-old Columbia River basalts with the younger Pliocene LKT lavas that are about 3 million years. So if the offset of these 16-million-year-old units, see the offset here, is the same magnitude as the offset in these 3-million-year-old lavas, well, then the faulting must have initiated after the emplacement of those younger lavas, after 3MA. However, if the offset in, lost my cursor, hang on, there we go. If the offset in, my cursor is not happy. Let's see if this one will work. If the offset in the older units is greater than the offset in the younger units, then you could estimate that the faulting had to have started before 3MA. So let's look at some geologic mapping here. And this is another cross section showing what we're looking at here. This is the kind of the Portland Basin on the west and the Yakima Fold Belt on the east. Here's some of the large mountains you may have enjoyed hikes, large mountain in Mount Defiance on the Oregon side. And you kind of see the arched nature of the Columbia River flood basalt as it goes through the Columbia River Gorge. And let me show you, I forgot to show you this. This is that same slope shade map where we've got CRB exposed in these deeply incised canyons on the cliffs of the gorge. And then up high, perched on top, are these lavas that unconformably overlie CRB. The LKT lavas outlined here in orange, and some younger Quaternary lavas outlined in purple. And so how do you find contacts between all of the members of Grand Ronde or the Wanapum basalt groups in a thick stack of lava flows like this, with these beautiful exposures in the Columbia River Gorge? It's challenging because in the field, most of these lava flows look almost exactly the same. And so we rely heavily on XRF geochemical analysis of samples to distinguish between different CRB units and also distinguish between the younger LKT lavas. So we combine our XRF data with magnetic polarity data, interpretations from LiDAR topography to draw contacts between the units within the Grand Ronde and within the Wanapum basalt groups. Okay, so here's a glimpse of our in-progress mapping near the northern end of the Mount Hood Fault Zone. The deep red purple colors show the CRB units in the cliffs of the gorge, and the younger Pliocene and Quaternary lavas that unconformably overlie them are in green and blue shades, located higher, perched high near the rim of the gorge. The small yellow dots on the map show our XRF sample locations and kind of give you an idea of kind of the density of sampling that's required to distinguish between different Grand Ronde units. More samples are in progress now. Okay, Duncan, if you can hear me, please hit mute on your microphone. Thank you. Okay, so a cross-section compilation of our team's geochemistry data shown here from west to east along the Columbia River and plotted at the elevation of their samples and colored by their geochemical similarities. This is also what guides our geologic mapping. And so you can kind of see the sub-horizontal nature of a lot of these geologic units in the Grand Ronde from west to east, and then they start to climb towards the Gate Creek Fault. And then you can start to see, just from the geochemical data alone, subtle east side down fault offsets across the Gate Creek Fault here, and these units here, and these units here. So our preliminary results showed magnitudes of about 150 plus or minus 100 meters of vertical separation in the CRB. And more analysis on especially on the east side of the fault here is going to help reduce the uncertainty in the offset estimate for these CRB units. But the Pliocene lavas, these units outlined in orange here, are also offset by the Gate Creek Fault. And so you can see in this LiDAR, see these cliff bands down here? These are a stack of 6 or 8 lava flows that are exposed by glacial erosion on the west side of the fault. And we're interpreting that these less obvious cliff bands down here are also the same LKT lavas. And the contacts these cliff bands are offset by several hundred meters vertically. And also we interpreted about 200 or 700 meters of right separation between the edge of the plateau here and the edge of the plateau up here. So we could be looking at total slip of several hundred meters if we think about kind of the oblique slip vector of those combined vertical and lateral offsets with slip rates that are kind of on the 0.1 millimeter per year slip rate, which is pretty typical for faults in this part of the world. So kind of a larger cross-section view, this is a cross-section from Jason McClary and his Hood River map showing the offsets of about 300 to 500 meters in the Hood River fault zone on the east side of the Graben. So we've got about 100 to 300 meters of separation east side down on the other side of the Graben, maybe about half as much offset as the opposite side of the Hood River Graben. So what does this mean? This means that because the separation, the vertical offsets in the 3 million year old units and the 16 million year old units are about the same, we tentatively believe that faulting here had to have happened after the emplacement of these 3 million year old lavas. And we're going to have improved this estimate with some new geochemistry results that we expect in the coming months. So let's now talk about how we can improve this estimate by characterizing fault offset in younger geologic units. And so here it gets again is that slope map of the Gate Creek section. And all these black lines are topographic profiles that I've taken across the fault zone to try to estimate the fault separation across the scarp. And this is about 2 or 3 dozen profiles I've done using a really nifty MATLAB script written by Cody Duckworth from Western Washington that basically uses Monte Carlo simulations to basically fit planar surfaces to the upthrown and downthrown parts of a geomorphic surface on 2 sides of a fault, and also fit a plane to the fault scarp itself. So this is a topographic profile taken across a large fault scarp. And here's a topographic profile taken across here. See this little tiny blip there? That's a very small fault scarp, maybe 1 to 3 meters high. So we did this a couple dozen times, and I'll show you the summary of those offset data in a moment. But one other cool thing to show you is in many places, the larger scarps, say 25 meters or so high. For example, here's a nice topographic scarp. Here's the top of the scarp here. Here's the bottom of the scarp down here. Somewhere in the middle of these larger scarps is another small scarp that is inset into the larger scarp. Sorry, folks, I'm a little delay here with my pointer. So here's this small scarp, and here's Ray Wells standing at the top of one of these, to be honest, not that impressive 1 or 2 meter high scarps inset into a much larger scarp that is much broader than the scope of this photograph. So this is hinting that there might actually be a very recent earthquake on this fault, because in an area where there's dense vegetation, thick soil formation, and really rapid hill slope processes, a tiny little scarp like this should be eroded away and blended in with the larger scarp, blended in with the background landscape quite rapidly. So the fact that this little scarp still persists, and we can see it today, suggests that the earthquake might have happened very short time in the past. So here's a summary of those topographic profiles, 30 or so topographic profiles, plotted from the Columbia River at the north end here for about 9 or 10 kilometers to the south. And the vertical axis here is the vertical separation. And so you'll see populations of vertical offsets, kind of larger vertical offsets that are observed in older glacial deposits that are probably pre-LGM, so pre-last glacial maximum, and lots of smaller offsets that are observed in younger geologic units, such as the glacial deposits that we believe are LGM, so maybe 20,000-year-old deposits. So we see a nice population of kind of 1 to 3 meters offset in these 20,000-year-old glacial deposits. And these are smaller scarps, so they're really good potential for paleoseismic trench sites, and we'll get to that in a little bit as well. So summarizing all of our vertical offset estimates for geologic units of known age, we can begin to characterize the history of fault slip on the Mount Hood Fault Zone. Offsets in late Quaternary units suggest a somewhat constant slip rate between 0.1 and 0.2 millimeters per year for at least the past 500,000 years or so. Sorry, I should have said the plot here this is vertical offset in meters versus time, or the age of the unit on the x-axis here. And each one of these data points are kind of summarizing the average offset in a certain geologic unit of a certain age. And vertical offsets in the CRB, so 16 million year old, and the LKT, 3 million year old, have a somewhat similar offset, like I mentioned earlier. And if you kind of take the mean value of that, this is the large uncertainty that we're going to try to beat down with our XRF data. It seems they have a kind of a similar offset. So one interpretation is that the fault actually initiated maybe 1 million years ago, if it's been a constant slip rate since its initiation, over its 1 million year lifespan. However, other slip histories are permissible, including a history that involves a gradual increase in the fault slip rate, possibly starting as early as 3 million years, and then increasing in slip rate in the last maybe 500,000 years or so. This latter interpretation would be similar to the 3 million year old initiation of the Hood River Fault Zone. That's the east side of the Graben that Jason McClary has documented in several geologic mapping efforts. So let's move on to when the most recent earthquake was. So this is a photograph of the just absolutely geomorphically gorgeous fault scarp cutting through the forest just north of Mount Hood, where here's Charlie Cannon from USGS and Ryan Levinson from Portland State standing at the top and bottom of this just immaculate, preserved, and very geomorphically youthful topographic scarp. So here the small scarp cuts through really young glacial deposits that we interpret to be LGM. Here's the slope shade map of this scarp. You see this tiny, very well-organized, single-stranded scarp going through this this cirque, which is the last glacial maximum cirque in Lindsay Creek, which flows downhill to the northeast into the Columbia River. So our trench site we've selected right here, which is the most ideal trench site that we found, was actually within the Hatfield Wilderness area, where backhoes are not allowed. So in September of 2020, after obtaining a special use permit from the Forest Service, we hand dug a paleoseismic trench across this scarp. Here's a photograph of the trench site just before we began digging. Here's Nick Roberts and Ryan Levinson, Portland State University grad students, standing at the top toe of this the scarp. Admittedly, here it's much less photogenic than that previous photo I showed you. Here is about 10 minutes after digging. We've got a bunch of happy grad students, and here is 2.5 days into the digging campaign, where we're all very tired but very excited to see a very gorgeous trench exposure and exposing the Mount Hood fault zone here. So this is kind of what a hand dug trench can look like, with large boulders up to 1 meter in diameter poking out of the sidewalls. We're proud to say this kind of looks like a backhoe trench in its size and shape, but it's obviously not, because these boulders would not have would have been plucked out very, very quickly with a backhoe. And so we were very happy to find, after 3 days of digging, a very obvious fault zone in the center of the scarp, cutting through these young glacial deposits. So what are we looking for in a trench? So before I show you some of the trench results, let's briefly discuss what paleoseismologists look for in the walls of a trench when there's been relative vertical motion across a fault. This diagram illustrates the basics of the colluvial wedge theory, where material from the up-thrown side of a fault ravels down onto the down-thrown side of the fault, where the new accommodation space was created during the earthquake. This occurs either rapidly while the ground is still shaking, or more commonly, this process occurs gradually via gravity-driven colluvial processes over the subsequent decades to centuries. You can imagine how the resultant deposit of colluvial material will be wedge-shaped, hence the name colluvial wedge, where its thickest portion is adjacent to the exposed fault free face and tapers to 0 thickness with some distance away from the fault. If more than one earthquake has occurred on the fault, you can imagine how multiple colluvial wedges, each related to a distinct earthquake, may become stacked on top of each other. So in this cartoon, here's one earthquake and the colluvial wedge that formed. There's a second earthquake, and then a second colluvial wedge formed, and then a third earthquake and a third colluvial wedge. So you could actually get stacked colluvial wedges. However, we chose a site with a very small scarp, hoping to only have a much less complicated relationship exposed in the trench wall with only one colluvial wedge. And so what do? We take tons of photographs of the trench wall, and we're using a new technique that I helped design during my postdoc at USGS, using structure from motion software like Agisoft to make a photogrammetric model of a trench wall. So the traditional method would take a bunch of photographs and try to stitch it together in Photoshop or with scissors, and then map your contacts and faults on this photo mosaic. The new method uses structure from motion technology and makes a seamless and photo-continuous model of trench walls. So here's kind of the before and after of this is kind of using the old method, where you can see kind of seams along edges of photos and different shading and lighting. And the Agisoft techniques kind of makes a continuous, nice 3D model that you can use to map your trench relationships on. So here's a photo mosaic derived from over 600 overlapping photos. This trench revealed indurated lodgement till down low, overlain by about 1 meter of meltout till. These glacial deposits are related to this Lindsay Creek drainage, where glaciers flowed northeast toward the Columbia River. We also noticed a 10 to 20 centimeter thick soil is observed just below the ground surface. And our draft trench log shows that we actually have part of this soil that goes underneath what we interpret to be our colluvial wedge. So we actually have along the fault zone here, we have a 10 to 20 centimeter wide fissure that's been filled with colluvial material, and then a wedge of deposits on top of that appears to have buried a former forest soil. The offset of the geologic contacts between lodgement till and meltout till have been offset about 1.2 meters, shown by these green lines, identical to the offset of the ground surface. So this tells us that we probably have one earthquake, and the ground surface has been relatively stable since LGM time here, maybe 15, 20,000 years ago. And the offset here has been the same between the geologic contact in the subsurface and the geomorphic ground surface as well. So we were delighted to find abundant charcoal in many of the geologic units, including the fissure fill and buried soil. Here is kind of that buried soil. Oops, lost my pointer. Hang on. Here we go. I'm back. Here's that buried soil. We kind of see a subtle brown and gray zone here, buried beneath the tip of the colluvial wedge here, which is kind of lighter and orange in color. Let's see if I can go back and forth and show you that. There we go. We interpret this charcoal-rich buried soil to be the forest floor before the day of the most recent earthquake. Following 1.2 meters of offset, material raveled from the fault scarp down onto the downthrown block and deposited this colluvial wedge. Therefore, if we can constrain the age of this buried soil and the age of this colluvial wedge, we can then bracket the timing of the earthquake. And so we collected charcoal samples from a lot of geologic units and cleaned them with water and tweezers, removing sediment and modern rootlets, and set them up for radiocarbon dating, carbon-14 dating. So here's kind of a summary of the carbon-14 results. And this plot here is going to show older geologic units at the top, it's a little kind of reversed than usual, and younger geologic units towards the bottom, just kind of stratigraphically here on the y-axis. And then their radiometric age on the x-axis here, with today being on the right side. So here's the oldest geologic unit. This is that we collected samples from, the meltout till, which again, this should be probably a 15 or 20,000 year old geologic unit. But the charcoal that we were picking out of it is somewhere between kind of 4,000 to 1,000 years ago. So this is probably preserving, the last few thousand years of bioturbation and charcoal being worked down into the upper part of this meltout till, even though it's much, much older in its actual geologic depositional age, probably 15 or 20,000 years old. Moving up section, the buried soil, come on, mouse critter. The buried soil here, which is at the top of this meltout till, you can kind of see there's a concentration of ages around 500 years ago. There we go. And so this is kind of a consistent population of ages in the buried soil from about, about 1300 to 1400 AD. Okay, so the next unit above the buried soil again is the colluvial wedge, right, and the fissure fill. And so just thinking about stratigraphic rules in geology, what should the ages in that colluvial wedge that's on top of the soil, should they be younger? I'd say so, because they're on top of the buried soil. But however, we were surprised to find all of the ages in the lowest part of the colluvial wedge and in the kind of distal part of the colluvial wedge were actually all older, even though they were on top of this buried soil. So how can this be? How can you have a geologically younger unit on top with older ages? Well, two things come to mind. You have kind of a large age range in the available charcoal. Imagine like a 500-year-old Douglas fir tree, by the way, spitting out 500 years of in age range of pieces of wood that can be burned, turned into charcoal, and incorporated into your colluvial wedge. Another process that's probably, I think, more applicable to the situation is that you actually have in the upthrown block, you're exposing some of this older meltout till. Remember, we've got 4,000 to 1,000 year old pieces of charcoal in the meltout till, and they're being exposed when you rupture the ground surface here, and they're contributing to the material that's being accumulated in the colluvial wedge. So we're interpreting that a lot of these ages that are surprisingly too old are simply just reworked out of this uplifted part of the meltout till and reworked down into the colluvial wedge. So then we took samples of the uppermost colluvial wedge, and we found that we actually can find some ages that actually post-date the buried soil here. And so if we kind of ignore and omit 9 samples that we think are reworked, we can actually bracket the earthquake quite tightly. And so this is this next plot is an Oxcal model, which takes into account all of the ages except for the ones we're going to omit, and tries to model an age using Bayesian statistics for the earthquake. And the most recent earthquake age model is AD 1363 to 1495. This is a 2 sigma range, and the mean of that is AD 1436. So therefore, it's a mere 500 or 600 years ago for this really large earthquake. So let's remember that age, that kind of 1436. Well, that's going to be an important number to remember. Oh yeah, really quickly, there is several lines of evidence for a minor component of right lateral fault motion as well. There's subtle evidence for dextral deflection of streams. We had evidence for right L shears that suggest dextral motion exposed in the trench. And we have right separation of bedrock drainages that are carved into CRB units. So maybe a kind of a longer lived representation of right lateral motion. So it might be dominantly a dip slip fault, but there might also be a component of right lateral slip here. Okay, so just with that, like with any trench, after you make a big mess and dig a big hole, you have to fill it back in. And here's some photographs of us backfilling and restoring the site. Fun fact, it took 3 days to dig the hole. It took 3 hours to fill the hole. Much more pleasant process. Okay, so let's jump to what's the earthquake magnitude and talk about kind of this idea of a fault segmentation for the Mount Hood fault zone. So I just told you kind of summary of the detailed summary of the Gate Creek trench study, which we have one earthquake about 500 years ago. The previous to this, there was only one other trench study on the Blue Ridge segment to the south, where 2 trenches were excavated, and they had an earthquake that was much older, prior to 11.6 thousand years ago, and maybe evidence for a younger earthquake, but not really conclusive evidence for a younger earthquake. And then just this past summer in July, Ashley Streig and myself and some of her grad students helped excavate a backhoe trench just south of Timberline Lodge on the south flank of Mount Hood. We already know from early results from this study that there's 2 earthquakes on this part of the Mount Hood fault zone. This is called the Twin Lakes segment. One event that has to predate what we're interpreting to be the Timberline eruptive event about 1,500 years ago, and a second, more recent earthquake that postdates Timberline but predates the 200-year-old Old Maid eruption. This is the Old Maid eruption that sent all that material down the Sandy River and made the Sandy River, why Lewis and Clark named it the Sandy River, because it shed out tons of volcanoclastic material into that watershed. That was from the Old Maid eruption about 200 years ago, 0.2 Ka. So we've got one event that's really young that could be the same age as this young earthquake on the Gate Creek fault segment to the north, but there's currently no direct evidence of this young earthquake on the Blue Ridge segment. So either it's true that that this younger earthquake actually did occur in these trenches, or because of the multi-stranded nature of the Blue Ridge fault segment, this young earthquake that we see on the north and we see in the south could have happened potentially on a different fault strand that was not studied during this trench investigation here. So maybe we have rupture on just the Gate Creek fault segment, which is only 15 kilometers long. Using the empirical relationships between magnitude and rupture length, this would suggest a magnitude 6.7 or so. However, this length of 15 kilometers for a single rupture is too short for a earthquake with 1.5 meters of displacement. So that kind of doesn't make the most sense. What if you had involved the Blue Ridge segment as well? Let's say you went through this segment boundary, and you involved a 25 kilometer long rupture. Well, that gets you up to maybe a 6.8, 6.9. And that requires that young earthquake coming through the Blue Ridge site that, as I explained, in some unknown way. But you could also have rupture that goes through this next segment boundary and involves the southernmost segment, the Twin Lakes segment. And you could actually get an earthquake up to magnitude 7.1 on a rupture that was maybe 45 or 50 kilometers long. And so, so we'll use that information in a moment when we start talking about how we'll evaluating how if the Mount Hood fault zone can cause earthquakes and can cause large landslides and other hazards in the Columbia River Gorge. So a really important and well-known landslide and well-studied is the Bonneville landslide, which is shown here on this map, the maps that I was showing earlier, but I think better illustrated in this really cool graphic by Washington DNR. The Bonneville landslide was an enormous landslide that blocked the Columbia River very recently. It's part of a much larger landslide, Cascade landslide complex, the Bonneville landslide being the most recent and probably the largest landslide in this landslide complex. Being shed from the Washington side of the Columbia River, where gently south-dipping bedrock repeatedly sheds landslides due to the dip slope nature of that geology exposed via incision of the Columbia River. This is also known as the Bridge of the Gods, where this man-made bridge here now mimics historical and indigenous records that suggested that folks could, prior to European colonization of the area, could walk from Oregon to Washington without even getting their feet wet, because this landslide basically formed a dam across the river. Well, this dam, it was probably about 75 meters high, which is about the thickness of the landslide deposit, and probably formed a lake. So here's kind of zooming out. Here's the landslide right here on a zoomed out map. Probably formed a lake that's 240 kilometers long, stretched maybe all the way back as far as near Wallula Gap. Jim O'Connor, my colleague, estimates that this lake, using estimates of modern day Columbia River flow rates, he thinks that a lake of this volume would only take 26 days or so of average river flow to fill this long dam, this long lake, and overtop this 75-meter high dam. So this probably only lasted for a few weeks or months, and the initial dam breach likely only eroded the upper part of this dam height, leaving a lower and smaller lake behind it. This lower and smaller lake apparently drowned and killed numerous trees along the riparian zone of the Columbia River. Here's a great photograph of by Lawrence, who studied these dead trees nearly a century ago. These trees were exposed during low river levels prior to the building of Bonneville Dam, the big man-made dam that now completely drowns this area with tens of meters of water. This map shows the distribution of these killed trees. So here's the Bonneville landslide, and all these little black blobs on this map are areas where Lawrence studied these dead trees. Recent reanalysis that's in review by Nate Reynolds indicates that some of the tree slabs, some of them actually collected by Lawrence almost 90 years ago, indicates that the trees died between 1426 and 1448. That's a 2 sigma range. Remember that the Mount Hood Fault Zone earthquake happened around the same time. Remember, there was a mean age of 1436, I believe, wanted you to remember. So look at the coincidence of these age ranges here. So got to ask ourselves the question, could a large earthquake on the Mount Hood Fault Zone could have triggered the Bonneville landslide, with its headscarp only located 17 kilometers to the west? Remember, the Mount Hood Fault Zone comes right through here. So to assess this question, we have run preliminary ground motion models. And our inputs for those ground motion models included a 45-kilometer long rupture with 1 to 2 meters of displacement on a magnitude 7 earthquake. And these models yield peak ground accelerations of about 0.2 or 0.3 G at the headscarp of the Bonneville landslide, Table Mountain. Although these PGA models are not conclusive about the landslide being triggered, it suggests that strong shaking might have triggered the landslide, particularly along the Washington side, where the rocks are densely fractured. There was pre-existing oversteepened topography due to the landslide complex, and incipient fracturing prior to this earthquake could have set up conditions really ripe for another landslide to happen in the event of an earthquake. So in summary, the most recent surface eruption earthquake on the Mount Hood Fault Zone occurred about 1363 to 1495 AD. The Bonneville landslide blocked the Columbia River around the same time. And finally, something I haven't brought up before, but a very distinct, oh yeah, sorry, I should mention, this also formed the Lake of the Gods. So the Bridge of the Gods was the landslide that blocked the river, and the lake that it was formed was the Lake of the Gods. It was about a 200 kilometer long or longer lake. And the data point I was mentioning that I hadn't brought up yet was there are flood deposits in the Portland Basin downstream of Portland that underlie a pumice that erupted from Mount St. Helens about 1480 AD. So these flood deposits may actually be a geologic record of the outburst flood that broke out from the Bonneville Dam being breached by the Columbia River. And the timing of them predating 1480 jives with all these other timing constraints. For example, here's all those data shown on one plot, where Time is going forward from left to right. These are calendar years in AD. So here's the time constraints from our trench. The Mount Hood Fault Zone happened ruptured between 1363 and 1495 AD. The Bonneville landslide, more tightly constrained due to dendrochronology, happened around the same time. And here's that flood deposit. It has to predate about 1480. So all these data suggest maybe an earthquake and landslide and flood all could have happened in the same time period. So that begs the question, are all of these events related? Are these cascading events that may have involved an earthquake triggered landslide, the flooding of a 200-kilometer long lake, and at least one outbreak flood, and they're all related to each other in a series of cascading hazards? Or alternatively, are these events completely unrelated to each other, and the Columbia River Gorge experienced, oh gosh, a decade or a century of terror with several unrelated natural disasters? That, of course, we can't say for certain. But what we can say is that about 500 to 600 years ago, this part of the Columbia River Gorge and the downstream and upstream parts of the Columbia River experienced several catastrophic natural hazards involving earthquakes, landslides, and floods. So this kind of highlights the integration of these unique but likely related events, highlights the importance of understanding the potential for not just a single natural hazard event kind of in isolation, but understanding the potential cascading nature of natural hazards and a kind of a more comprehensive and holistic approach to understanding natural hazards in general. I will say that just a month ago, Pat Pringle and his colleagues like Nate Reynolds published an even more detailed update for this the Bonneville landslide in a GSA talk here in Portland 1 month ago, where they've narrowed down the Bonneville landslide to a single growing season, the winter season of 1447 to 1448, using really detailed dendrochronology. So that's out, and it's GSA abstract at this point. And so this is even going to kind of tighten the time constraints on when the potential relationship between this earthquake and landslide and floods occurred. So really exciting results from Pat Pringle and his team about the Bonneville landslide. Okay, it's time to sum up and put things in regional context here for the Mount Hood Fault Zone. The Hood River Graben I've been talking a lot about, which is, again, the east side is the Hood River Fault Zone, and the west side is the Mount Hood Fault Zone. You know, is it a simple kind of two-sided graben? Well, there's a lot of these north-northwest trending faults that kind of cut through obliquely through the graben as well. These are big fat red lines that I've kind of used to kind of highlight kind of the major structures that make up this part of the High Cascades graben. And so, you know, this could, instead of being a simple kind of north-south oriented graben that accommodates east-west extension, it could also be accommodating kind of a component of northwest translation, which is a common phenomena in this part of the Pacific Northwest. So, you know, one explanation is that you could actually have a step over between these northwest trending right lateral fault zones, and that kind of releasing geometry and extensional step over could drive the formation locally of a graben. And maybe that's why these grabens along the High Cascades are more discontinuous in nature. And another point I'll bring up is, you know, the stress field, this kind of regional clockwise rotation that I showed in the first couple slides, you know, that Tom Broker map and the maps by Ray Wells and whatnot. You know, that stress field doesn't appear to have changed over the last 16 million years, but maybe the style of deformation that accommodates that stress, maybe that has changed. In other words, you know, maybe prior to 3MA, you had Yakima style folds going through this area, and we have them cutting through the Cascade Range. And maybe those folds are accommodating the north-south shortening. But maybe when the rift propagated from south to north, Yakima folding gave way to more of a transtensional style of deformation, accommodating a similar kind of regional clockwise rotation. So these are all kind of incipient ideas that are, you know, kind of in the abstract and meeting presentation form right now that we're all working on. Here's just an example of kind of just east of the Hood River Graben of a lot of these northwest trending structures that are thought to kind of post-date and offset the Yakima folds. You know, think features like the Warwick Fault that offset the kind of the Horseheaven Hills anticline and the Columbia Hills Fold. work that folks like Daniel Woodring's been working on recently. So this is kind of just hot off the press. Some work that Ian Maiden has been kind of spearheading along with myself and Ashley Strike. Here's a map showing we just got some new LiDAR in several patches along the crest of the Cascades, and Ian's been feverishly mapping scarps on this LiDAR. Here's Mount Hood, and we've been talking about these segments. The Gate Creek fault segment is just on the north edge of this little map here. But if you continue to the south, you kind of see this alternating pattern of north-south faults and north-northwest trending faults, and north-south faults and north-northwest trending faults. So maybe these scarps are actually reflecting this kind of transtensional and segmented nature to the fault systems along the crest of the Cascades. And here's kind of a schematic of that, where you might have these northwest trending fault systems like the Sisters and Brothers fault zones coming into the hot and warm Cascade arc. And before they pass through the arc, maybe they step over in a releasing step over and accommodate and host these large stratovolcanoes before they punch out the other side of the Cascade arc and do a lot of these faults that we know so well, like the Portland Hills Fault and the Gales Creek Fault. And so at the latitude of Hood River, you might have these northwest trending faults like the Dog River Badger Lake fault zones that come in, step over across the Hood River Graben and punch out the other side into the Wind River fault zone that goes up into the Mount St. Helens seismic zone. So maybe this is a kind of a structural model to consider that could explain the observations of both east-west extensional faulting and north-northwest strike slip faulting as it transects obliquely across the Cascade arc. Okay, last slide summary. The Mount Hood fault zone is on the west side of the Hood River Graben. It's a long 60-kilometer long fault zone that may have initiated in the last 1 to 3 million years. It's got a really young earthquake, only 500, 600 years ago. It's the same time as the Bonneville landslide. And the Hood River Graben may accommodate both this intra-arc rifting, but also northwest translation of rotating crustal blocks in the Pacific Northwest region. Thank you very much.
Yay, I think everybody's clapping. Woo! That was great, Scott. Oh man, it has been too long since I've heard you speak and heard your wonderful words. Very good.
Thanks, Chad.
No, thank you. I love how you brought it back all into the model too. And I saw Tom was even at the talk too.
Oh, great.
But let's open this up for questions. Anybody, you can just unmute yourself, feel free, or raise your hand, I'll unmute you, but I think you can just do it. Anybody have any questions?
Yeah, I can't see the chat, so if anything pops up in there, let me know.
Okay. Trying to keep it all together. It was pretty awesome. We saw Spokane Falls Community College had a whole class here. Yeah.
Oh, cool.
Go, Jennifer. So where are you guys mapping? Oh, Tom's got a question. Good. All right.
There, now you're on.
Hi, Scott. Tom here.
Hey, Tom.
How are you doing?
Good, man. Good to hear from you.
Yeah. You know, this landslide is very interesting that you talk about it. As you know, in the 1872 earthquake, there was another landslide, damming of the Columbia River.
Right.
That one only lasted a few hours, maybe 12 hours or so. But it just occurred to me that this phenomenon might be fairly frequent.
Yeah, right.
After large earthquakes near the Columbia.
I agree. And you know, this let's see, I'll switch this photograph. This is maybe real world view. That Cascade landslide complex. You can kind of see this kind of low relief hummocky topography here. This, you know, the Bonneville landslide is just one of dozens, if not hundreds of landslides here. So, you know, yeah, you've got a continental scale river carving through an arc and uplifting an arching arc. And maybe that's driving the steepness and erosion and landsliding. But you know, you've got these earthquakes like the Portland Hills Fault and this Mount Hood fault zone nearby too that might be driving a lot of these landslides as well. See, I think I saw Mark physically raising his hand. Is that true, Mark?
Well, I was, and then Tom sort of asked the question that I was wondering about, and it was essentially, by the way, wonderful talk. That was really, really fun to watch.
Oh, thanks.
Is with your higher resolution mapping that you're doing at 1 to 24K,
Mhm.
Do you think that you'll start maybe creating these landslide bullseye maps around some of these faults that you can actually look at tying the strong ground motion to the landslide occurrence and maybe dating those?
Oh gosh, that's a really good question. And there's tons of people who are much more focused on landslide mapping than myself. Folks like Josh Roaring in Oregon and folks in Dogami and DNR at the state agencies that are doing a lot of landslide inventory of various areas. We aren't really seeing a high density, an increased density in landslides as a function of proximity to a fault right now. It looks like there's a lot of other lithologic drivers and erosional drivers for a lot of the landslides we're mapping. But to be honest with you, we haven't tried to actually quantify that. Is there an increase? I say that we don't see it because it's not jumping out at us, but we actually haven't interrogated that in a kind of quantitative ways. But that might be interesting to see, kind of present like a density map, right, of landslides and see how that relates to the proximity to fault traces.
Yeah, that would be great.
Yeah, it's a clever idea.
Yeah, wonderful. Thank you.
Yeah, thanks for coming.
And Pat Pringle had something in the chat there. The tree ring date is during dormancy between the end of 1446 growing season and the beginning of 1447.
Yeah, in the winter. No, yeah, I misspoke when I first said growing. Yeah.
Oh, life's good. So how does your graben, I like that when you put it all in the context there at the very end. How does it look like it's actually sort of narrowing towards the north at all? I mean, if you kind of take a step back there to go back to Rick's.
Yeah. So the idea that Rick Connery has had for a long time, and I kind of like it, is that the graben's been kind of unzipping from south to north over time, and that kind of makes sense if you're. Let me see if I can do this for your perspective. If you have the Oregon Coast Range here, rotating out and sliding up, it kind of makes sense that faulting would start in the south first and then propagate to the north, right? As you kind of rotate this block away and up. So I don't think there's actually like a widening of the rifts as so much to the south, as much as kind of the timing supports that. So I think the graben in the south, kind of towards like Three Sisters latitude, just west of Bend, northwest of Bend, it's still kind of on the 20 to 30 kilometer width. It's similar to the Hood River graben up here, but I think the timing is different. And actually, I don't know the answer to this, but I would speculate that the offsets might be greater as well. Because if you have a fault system, even these kind of really slow slip rate faults, like 0.1 millimeters a year or whatever, going on for 7 million years versus 1 or 3 million years, they might have larger total offsets. That's what I would predict, but I actually don't know if that's true or not. But that would be that'd be a good thing to test the hypothesis of the kind of northward propagating rift system.
Fair enough. All right. Do we have any more questions? I know we have most of our students have probably moved on to class at 1 o'clock, but I'm glad that the ones that were there could hear this wonderful talk. And if it's okay with Scott, we'll post this lecture up on YouTube, on the EW Geology Rocks YouTube, with some other great talks like Tom's.
Sounds great. Thanks, Chad.
Yeah, so thank you very much. I hope everybody has a great day. Merry Christmas, Happy New Year, Happy Holidays. And we'll see you next year, hopefully. All right.